right, ladies and gentlemen, today's class recording has started. So, yesterday, we did our introduction to bonding. Let's talk about that first. What is a bond? You can read it right from the outline if you would like. What is a bond? Go ahead, Chris.
Attractive force that holds atoms.
An attractive force that holds atoms together. That's what a bond is. But more importantly to our discussion, why do atoms bond with one another? Eric, go ahead. They're trying to get 8 valence electrons. And why are they trying to get 8 valence electrons? A stable or a low energy state, right? It always comes back to energy. Things, that includes atoms, will do whatever they can to get to a lower energy state. And for atoms, 8 valence electrons is a low energy state. That being said, 8 valence electrons, right? What are valence electrons? Electrons in the highest energy level. And, sorry, I should have had this up already, but we'll go here, oh, here, nope, there, oh, had it. Okay. We said, as we looked at the periodic table, there is a pattern as far as the number of valence electrons is concerned, right? Group 1 are alkali metals. How many valence electrons do they have? 1 valence electron. Group 2 has 2 valence electrons. We said for our purposes, we're going to skip our transition metals, so groups 3 through 12 we're not going to worry about, right? Group 13 then has 3, 4, 5, 6, 7, 8, right? Okay? I'm not sure why it says 0 on top there. Like, that doesn't make sense at all. Okay, but I don't know. We said that in order to get that stable electron configuration that has 8 valence electrons, one of two things can happen, right? How can atoms get to 8 valence electrons? Gain or lose? Julia, which types of elements will gain electrons? Nope. Non-metals will gain electrons, right? Over on the right-hand side, atoms that already have 5, 6, or 7, right? It's easier for them to get up to 8. But then that means that on the left-hand side, our metals, they're going to do what? Lose electrons, right? And so they end up basically losing their valence electrons, so that takes them down a level, but they still have that level full because they had to fill it up before they went to the next one, right? Good there? Good as far as an overview goes? Okay. All right, so let's get into the actual business of forming an ionic bond. And so we are going to start here. All right. So how does the bond form between sodium and chlorine? Sodium and chlorine forms a compound that sodium and chlorine form a compound that you are pretty familiar with. Does anybody know what compound sodium and chlorine form? Sodium chloride, which is salt, right? Okay, salt that you have on your table. Okay? So, I've started off, and I've drawn for you 2 Lewis structures. The Lewis structure for sodium and the Lewis structure for chlorine. Are we good with how those Lewis structures came about? Right. Sodium, being in group 1, has 1 valence electron, so I gave it 1 dot. Chlorine, being in group 17, halogens, I gave it 7 dots. Okay? Julia, what's going to happen here? What is sodium looking to do with that 1 electron? Lose its electron, right? What is chlorine looking to do with its 7 electrons? Gain an electron, right? So this is a pretty convenient situation for these 2 atoms, right? Ready? So sodium has 1 valence electron. It's looking to lose that 1 valence electron. Chlorine has 7 valence electrons. It's looking to gain 1 to get itself up to 8. Okay? And so, right? Oh, you guys are writing some things down. I don't want you to miss this, but it's pretty awesome. Yeah, the lame animations. But back, like, PowerPoint 2000, this was... So. Okay. All right, good there? Stop. Why would you All right, so in this case here, like I said, a pretty convenient situation because sodium is looking to lose one electron, chlorine is looking to gain one electron, and so this happens, right? Ready? Don't miss it. Don't blink. Ready? Here we go. Oh. Whoa.
Yeah.
Alright.
What do we do? Draw an arrow.
What? You can draw an arrow if you would like. Yeah, you'll see how I do it. So usually I circle that one electron and then draw an arrow to like bring it over to the other side. Okay. So. All right. So now this has happened, but according to our definition, is this a bond?
No.
No. Okay. All we've done so far is to do what? What has happened because of this transfer of an electron? We made two stable atoms, right? Or two lower energy state atoms, because now both of them have 8 valence electrons. If you look at your periodic table, I won't make you do this, all right? I won't make you figure this out. I'll just tell you. If you look at your periodic table, chlorine has its 3rd energy level full, okay? Because it's in the 3rd row, yes? Sodium has its 2nd energy level full. Because it had only 1 electron in that 3rd energy level, it lost it, so now its 2nd energy level is full, okay? But, Chris,
Yeah.
at the very beginning of class, you told us that a bond is what?
Attractive force that holds atoms.
An attractive force that holds atoms together. So let's
Yeah.
talk about where that attractive force comes from, okay? Metals lose an electron. Back when we were discussing electricity, right? Things that lose electrons end up being what? Positively charged, right? So, metals that lose electrons form what we call cations. It's not a cation, it's a cation. Okay? I know, it looks like cation, but it's a cation. Okay? Alright, so main group metals, so again, not our transition metals, but our main group metals, will lose their valence electrons and form cations. Cations have more protons than electrons, because what have they done? They've lost an electron, or sometimes more than 1 electron, right? Because they have lost electrons, they now have a positive charge. This process of losing electrons we refer to as oxidation. So any atom that loses electron we say is oxidized. Good. Forming rust is forming a bond between iron and oxygen. So that process is involved there. Yes. Okay. All right. Good with metals. Okay. So then that means non-metals are basically going to do the opposite of this, right? So non-metals form anions, not anions. So non-metals form anions. Non-metals gain electrons in order to achieve an electron configuration similar to the next noble gas, right? 8 valence electrons. Anions have more electrons than protons, so they have a negative charge. When something gains electrons, we refer to it as reduction. Don't ask. There is a reason why, but it's a little bit beyond the scope, right? I'm assuming some of you are saying to yourselves, well, why would you gain electrons and call it reduction? But there's something else that's going on there. And so, we have metals forming cations. Cations have a positive charge. We have nonmetals forming anions, which have a negative charge. Any atom that has an imbalance of electrons and protons regardless of whether it has more protons than electrons or more electrons than protons, generally speaking, we call that an ion. So it's not an atom anymore. Atoms have equal number of protons and electrons. Once we start trading, we refer to those things as ions. But because ions have charges, what do they do to each other?
Attract.
They either attract or
Repel.
they can repel, depending on whether they have the same charge or opposite charges, right? So, let's go back to this picture. And I think this starts the third page, right? So, at the beginning, before this happened, how many protons did sodium have? 11. Right? Because that's that's sodium's atomic number, right? How many electrons did it start with? 11, because you got to match, right? But now, how many electrons does it have? 10. It has 10, right? It lost one valence electron, but it still has 10 electrons, right? Sodium now has 11 protons, but only 10 electrons. If it has 11 protons, but 10 electrons, what kind of a charge does it have? Positive. So we call it now a cation, right? So let's talk about chlorine, right? How many protons does chlorine have? 17, because that's its atomic number. But now, how many electrons does it have? It has 18 electrons, because it picked up one from sodium, right? It starts with an even number, but now because it's picked this electron up, it has more electrons than protons. Chlorine now has 17 protons, but 18 electrons. So what kind of a charge does it have?
Negative.
It has a negative charge, so that makes it an anion. It has to come back. Cation and anion come from, Chris, the idea of a battery. The two sides of the battery, one is a cathode and one is an anode. And that's where cation and anion come from. Because we knew about batteries long before we knew about cations and anions. And so which one of them comes out of which side of the battery, that's how they got their name. Okay. All right, so if you have a positively charged cation and a negatively charged anion, what are they going to do? Ready? Watch. Whoa, look at it, right? The negative charge on the chloride anion and the positive charge on the sodium cation attract each other and form an ionic bond, right? That's where the ionic bond comes in. The attractive force that results after we have traded electrons. The bond is not the trading of electrons. The bond is the attractive force that comes after the trading of electrons. Okay? Good. Yes, and we'll talk about that in a second when we get into naming things. Okay, yeah. Notice it says the negative charge on the chloride anion as opposed to the chlorine. There's a reason for that, and we'll talk about that when we get into naming a little bit later on. Okay. All right. Good there? Okay. So, ionic bond. Negative charges are attracted to positive charges, but that also means that negative anions are attracted to positive cations, right? Just because we're talking about one single atom versus a whole big thing doesn't change the fact that positives and negatives are attracted to one another, okay? The attraction between negative anions and positive cations is an ionic bond. Remember, the bond is an attractive force that holds atoms together. Ionic bonds happen after the transfer of electrons. So it says, ionic bonds happen after the transfer of electrons from a metal to a nonmetal and the formation of ions. Sometimes we can look at a compound, a group of atoms that have been bonded together, and just by the type of atoms that are in it, we can tell what kind of bond it is. Ionic bonds always form between metals and nonmetals, because one of them is looking to lose electrons and one of them is looking to gain electrons. Jack, go ahead.
We have like a element from like group 2 and an element from 17.
Hold on. We'll get into that. We'll get into that right now. Is that okay? Frank, go ahead.
So the metal has 7 valence electrons.
Metals won't have 7 valence electrons. Okay? Is that? Okay. All right. Good there? Okay with that? Okay. So, let's pull out this sheet that I gave you today, or that Joe handed out to you at the beginning of class. So it says ionic compound formulas up at the top. And let's take a look at some practice problems. All right? And see how this all works together. So, let's go here. Bring this down here, or not, whatever. All right. So I'm going to go here. No, that's not what I'm going to do. I'm going to go here. And just for practice, and to illustrate one other thing, okay, let's pull just this first one. All right, so for the first couple, let's go through all the steps. You might get to the point where you don't have to do all of these steps, but because we're just starting off, let's go through all the steps, right? So, 2 elements, potassium and iodine. Let's start with Lewis structures. First, where is potassium? Well, its elemental symbol is K, right? And what group is it in? Group 1's. How many valence electrons does it have? 1, right? So there's its Lewis structure. Okay? Iodine. What group is it in? 17. What's its symbol? I. And it has how many valence electrons? 7. So I'm going to draw them here, 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 and here. Okay? All right. So, just like we saw in the previous example that we did with sodium and chlorine, right? If sodium and chlorine form a bond, potassium and iodine are going to form a similar bond. Why? Same groups, right? Remember, things in the same column, in essence, do kind of the same thing, right? So, we're going to see this transfer from here to here. Okay? All right. After that transfer, right, which element formed the cation? Potassium. Okay? So now here's where things get a little bit, not tricky, but we have to remember some things, all right? So, potassium forms the the cation, okay? What is this ion's name in symbol, all right? When metals lose their electrons, they go from being atoms to ions, right? So this, after we transfer the electron from here to here, this is now a potassium ion. Okay? Doesn't seem so hard. As far as its symbol, we still use its elemental symbol, but we have to indicate its charge. And so, as a superscript up here, we'll indicate its charge. Depending on which book you look at, this isn't like important or anything. This isn't going to be like a bunch of stuff on your test that you're going to have after spring break, you know. So, you might want to pay attention. Just throwing it out there. So, for potassium, it still has 19 protons, so that's why it still has the symbol K. But we'll indicate its charge with a superscript. Depending on what book you use and what book you read, sometimes they do it differently. This is how I usually do it. 1+. Sometimes some books will just write plus, okay, but we'll see that sometimes there's a number involved with it. So I try and just get in the habit of using the numbers to begin with. Okay, so potassium is now 1 plus, indicating that if it has a positive 1 charge, how many electrons has it lost? Just 1. Okay. All right, let's talk about iodine. Okay, so by process of elimination, if potassium formed the cation, that means iodine is going to form the anion. But also, because what is iodine doing in this situation? It's gaining electron, which means it now has what kind of a charge? Negative charge. Julie, go ahead.
Wait, so typically would a metal use a cation?
Not typically. Typically is not a strong enough word. Always the metal is going to be the cation, because metals are looking to do what? Lose electrons. Yeah. Metals are always going to be the cation because they're the ones that want to lose those electrons. Non-metals are always going to be the anion because they're looking to gain electrons. Okay? But how we name these things changes for the anion. So, Frank, you asked me about the chlorine being chloride. This is what we do. When our non-metals gain electrons, they go from being atoms to anions. But we call them differently, just for the negatively charged ones. Don't ask why, because I don't have a good answer for you. Okay? So, instead of this being iodine, when a non-metal gains electrons, its ending changes to IDE. So this, after the gaining of electrons, we call it iodide. It is an iodide ion. Okay? As far as its symbol goes, it still has 53 protons, so it's still iodine, or we use the symbol I, but now, just like on the potassium ion, we indicate that it has a charge with the superscript. So we go 1 minus for the iodide ion. Okay. All right, good so far? Okay, now let's handle the next 2 parts on the right-hand side. Formula and name. According to our Lewis structures, potassium had to lose 1 electron, iodine had to gain 1 electron. So everybody's happy with just this 1 electron transfer. Does that make sense? Everybody's got their 8 valence electrons, everybody's good. So we only need a 1-to-1 ratio of potassium to iodine to make everybody happy. So in the formula shows the ratio of the atoms that we need to get everybody their stable electron configuration. Okay? Formulas and names follow the same pattern. And on the back of your outline, or on the back of the outline that we filled out yesterday, you have these rules. I'm just going to tell you them now because they're not really that hard to remember. But okay. So, whenever we're writing formulas and names, cations always come first, anions come second. All right? So, Julia, getting back into our cation anion. What's the first symbol that we're going to write in our formula? K. Okay? Now, the formula doesn't tell us charges, it tells us ratios. We only need 1 potassium, and I didn't connect my K, so I probably should. We only need 1 potassium, so we don't really do anything. The fact that we wrote the symbol indicates that we have 1 of those potassiums, okay? And then the anion comes second, so the formula for this compound is Ki, indicating that we needed 1 potassium and 1 iodine to get everybody their stable electron configuration. Okay? Good there? As far as the name goes, order stays the same. Cation first, anion second. So the name of this compound will start with potassium. But then for the anion part, we use its anion name. So this is not potassium iodine, it's potassium iodide, indicating that the iodine has changed from an atom to an anion. Okay? How's that for starters? Good? Okay. Let's try the second one on the list. And so, Jack, this is where we start getting into that question from before. Okay? All right. So, let me grab this. Okay. All right. So, let's make this a little bigger so I have some more space to write. Okay. So, strontium and fluorine. Find strontium on the periodic table. What group is it in?
Second.
It's in group 2. Everybody find strontium there? Okay. Indicating how many valence electrons will it have? 2. Okay. So strontium has 2 valence electrons. Okay. Joe, where's fluorine at? 17, right? How many valence electrons does it have? 7. All right. 1, 2, 3, 4, 5, 6, 7. Okay. All right. Julia, what's strontium looking to do in this situation? Lose electrons because it is a what? It's a metal, right? What's fluorine looking to do in this situation? Gain 1. Okay? So gain because it's non-metal, right? Okay, so this is going to happen first. Okay? So here's where this problem becomes a little bit different than the problem we just did, right? Fluorine's good, right? It's got its 8 valence electrons. Is strontium good?
No.
Nope, right? Strontium has to lose 2 valence electrons. So this transfer of an electron from strontium to fluorine works for fluorine, but it doesn't quite work for strontium, right? So, what comes along? Another fluorine comes along, right? Joe, how many valence electrons does this fluorine have? 7. What is it looking to do? Gain how many? 1. Luckily for that other fluorine, this strontium has another 1 to get rid of. So another transfer of electrons happens just like that. Okay? Does that make sense? Okay, let's do the middle part. Julia, which element formed the cation? Strontium. Okay? So, strontium is our cation because it lost electrons. So now it's a strontium ion. As far as its symbol goes, it still has the same number of protons. It still has 38 protons. So we can use SR. What kind of charge does it have now? Well, it has a positive charge, right? But how many electrons has it lost? 2. So it has a +2 charge. We indicate that with a 2+ superscript. Okay? That good there? So then the anion in this case is fluorine. Okay? But because it has lost electrons, Joe, now it's what? Fluoride. Okay? Something to keep in mind, look at fluorine on the periodic table. Look at its name. How is it spelled? F-L-U-O. All right? Okay, so make sure you don't spell it F-L-O-U. All right? Okay. So it is a fluoride ion. Now, individually, right? Both of those ions still have 9 protons, so we can use the F, but they've gained how many electrons? Individually. Just 1. So each ion is a -1. Okay? Say again? No. That's where the formula is going to take care of this. Okay? So now, we said the formula shows us a ratio. A ratio of how many atoms we need so that everybody gets their stable octet, their stable electron configuration. Okay? Back over in our Lewis structures, how many Lewis structures of strontium did we have to draw? Just one. But how many fluorines did we have to draw? 2, right? So, we indicate that in the formula. What symbol is coming first in our formula? SR, because it's the cation. So we'll start with SR. F is going to come second, but we have to show the ratio. We show the ratio with subscripts. Okay? So how many fluorines did we need? We needed 2, so our formula looks like that. The fact that we wrote strontium indicates that there's 1 atom. If there's only 1 atom here, we don't have to write a subscript 1 here. The fact that we wrote the symbol indicates that there's 1. The 2 comes in because we needed 2 fluorines. Eric, go ahead. Say again? Below, yes. Subscripts when we're talking about formulas, okay? So then, for the name, now this gets can be a little confusing, okay? We still start off with the name of the cation first. So, strontium, but then we just use the name of the anion. There's no indication in the name that there are 2 fluorines there. Because whenever you join together strontium and fluorine, it always has to be this combination. Okay? Good there? Here, let's do one more real quick before the end of the period. I'm just going to write it up on the board so we don't have to go through it step by step, but follow along and hopefully you'll end up with what I ended up with. All right, so let's go here. The next one up is sulfur and sodium. All right. Okay. So, sodium, group 1, it has 1 valence electron. Sulfur, group 16. It has 6 valence electrons. Okay? As far as the transfer goes, sodium's looking to lose this electron. It goes over here. Right? But sulfur, because it had 6 valence electrons, still needs to gain 1 more. Another sodium comes along. All right? That's what we end up with. Okay. Does that make sense? Tomorrow, we will do some more practice of these in class and talk about names and formulas for ionic compounds. And then we'll finish up tomorrow, or at the end of class tomorrow, I'll put up your quiz on ionic bonding so you can finish that up sometime over the spring break. Right?